Hey kids, so I'm going to start with this so that you can maybe understand this a little better than we did on the last video, and I'll cut that out. All right, um, molarity. So when do we use molarity? Molarity is moles of solid per liters of liquid. And we're going to need this when we are doing problems that involve having a solid, in this case hot chocolate here, and you're weighing that out. All right, so you weigh out a solid and then you add solution. So we did this in the lab with lemonade. We put solid into a cup. We filled the cup up to a certain level. There was a line in there indicating how much solution it was, and then we put the liquid up to that point, and then we knew that's how many liters of solution we had. So that's when you're going to deal with this, when you have solid and you're dissolving it in liquid. So in this case, the moles of solid we don't have. We have 25 grams of NaCl. So we don't have moles, but we do have the liters, 2.5 liters of solution. So we already know the bottom part of this is going to be 2.5 liters of solution. And what we need then is the moles of solid. And how are we going to get that? We're going to use that 25 grams. So 25 grams of NaCl. And we need to get that from grams to moles. And we do that by going to the periodic table, and we get that gram to mole relationship. So sodium is 23 and chlorine is 35.5, and there's one of each of them. So we can add that up and we get 58.5, and that is the grams. So 58.5 is the grams from the periodic table. And the moles on the periodic, that's 1 mole. 1 mole of sodium chloride will weigh 58.5 grams. So we take 25 and we divide it by 58.5, and we get 0.427, so 0.4277. And now we have our moles, and we put that on top, and we divide 0.427 divided by 2.5, and we get our molarity is 0.17. So that's the molarity of that solution. Should be 0.71 if you're doing significant figures. All right, so that's an example of when you use that. And here's another example, which I'm pretty sure I worked out on the board. But here, we want the concentration, so the 1.25 molar is given. And we have the liters, so we know that it's 3.00 liters. And again, we're looking for the moles, but in this case, the grams. So we'll solve for moles, and then we'll convert that to grams using the periodic table. So to isolate this X, so to isolate the X moles, we need to multiply both sides by 3 liters. And when we do that, these will cancel, and we will get 1.25 times 3, and I've done this enough. Actually, it's 3.75. So that equals 3.75 is equal to the moles. So we're almost there. This asks for grams of KNO3, not moles. So we need to go from 3.75 moles to grams, and we do that using the periodic table. When you need a gram to mole relationship, you go to the periodic table. So potassium is 39, and I'm doing this without anything, so hopefully this is right. Nitrogen is 14, and oxygen is 16 times 3, which is, so that's nitrogen equals 14, oxygen equals 16 times 3 of them in this case. So that is 48. So 48 and 14 and 39, when we add all those up, we get 3 and 8 is 1, carry the 1, and yes, I was hoping that was the case, and it is. No, it isn't. For 39, 9 and, oh, I'm sorry, 9 and 4 is 13. 13 plus, so it's 21, so carry the 2. There we go. So it's 101. Good. So it's 101 grams in 1 mole, and so 3.75 times 101 is 378 grams. So we have figured this out, that it's 378 grams of KNO3. All right, so that is that. Now, when we do these diluting solution problems, we're making a concentrated solution more dilute by adding solvent. The example we did in lab was this. When we had our squirter, our little bit of flavor enhancer, we're adding to water. You could tell how concentrated that is. Look how deep purple it is, but when you dilute it, it becomes much lighter purple. So that is what we're doing when we're doing these diluting problems, is M1V1 equals M2V2. So we're adding solvent to a concentrated solution. The concentrated solution typically goes before. It kind of doesn't matter which side you put it on, but usually the M1V1 would be the concentrated molarity and the concentrated volume, and the M2V2 would be the diluted molarity and the diluted volume. And usually you have 3 of these and you need to find the 4th. How this all works is the molarity times volume before the dilution equals molarity times volume after the dilution, because if you remember, molarity is moles over liter, and when you multiply that by liters, that'll give you moles. Same will happen on the other side, moles over liter times liters, that'll give you moles, and moles equals moles. So that just basically says the amount of squirt that we put in here is equal to the amount that's still in the cup after it's diluted. And that's true. How much concentrated stuff you put in is equal to how much is in there after it's been diluted. The key with these, you're never wrong to put everything into liters for this test. But for these M1V1 equals M2V2, for math reasons I won't get into right now, but it's true. You can either keep it in liters or milliliters, the volume. Just make sure they're both the same. They will cancel. So if this molarity times milliliters equals molarity times milliliters, the milliliters on each side will cancel out. So you can keep it in milliliters if it's in milliliters. You're never wrong to convert everything to liters, and it's not bad practice. So in this case, we have 12 molar HCl. That's concentrated HCl. So our M1V1 equals M2V2. Our M1 now is 12 molar. And we're looking for how many milliliters of it, so we don't know the volume of it. We're going to make 1.25 liters. So our second volume is 1.25 liters. Keep in mind, this is in liters. And then 3.25 molar would be that second molarity, 3.25 molar. So keeping in mind, this isn't pretty, but I guess it's not bad. I did try to buy another stylus, and they didn't have anything for me. Plus, I forgot my wallet, so it wouldn't have mattered. But they didn't have anything for me. All right. Back to this. So 12 molar times V1 equals 3.25 molar times 1.25 liters. When we solve for V1, we are going to find it in the unit of liters, because that's what this unit is, and I apologize for that. So 3.25 times 1.25, 3.25 times 1.25 gives us 4.06. So this side is 4.06, and that is, as we talked about, moles, because when you multiply molarity times liters, you get moles, and that will equal 12 moles per liter times V1. So we need to isolate that V1. This is our X, so we divide both sides by 12. So 4.06 divided by 12, and we get 0.339. So V1 equals 0.339. And again, the units of this are going to have to match the units of what we started with, which is liters. Now, this question asks for milliliters, so you will need to convert to get full credit. And convert liters to milliliters, you got to jump 3 times, 1, 2, 3. And hopefully you realize you need a larger number because milliliters are smaller. So it's a bigger number. 339 is bigger than 0.339. All right, so that's that example. Example 2, adding 25 mils of water to 125 mils of 0.15 molar NaOH. What will be the molarity of the diluted solution? So here is one solution. Hopefully you can see these two things are connected. We have 125 milliliters of a 0.15 molar NaOH solution. And that's going to equal the molarity, which is what we're looking for, molarity. So our M2 and our V2 is a little tricky because it's adding 25 mils. You have to read these problems. So adding 25 mils to 125 mils is 150 mils. So this second solution will have 150 mils in it, 25 more than what we started with. Now again, you're just going to solve for this variable. So you multiply 125 times 0.15, and that gives you 18.75. And that's going to equal M2 times 150. These units are milliliters. These units are milliliters, so they're going to cancel. It's okay. 18.75 divided by 150 gives us 0.125. So M2 is equal to 0.125, and that unit is molarity, M. All right, so then we talked about colligative properties, and colligative properties are properties that happen when you add a non-volatile solute, so something you're dissolving that's not going to leave the solution, one that won't evaporate, to a solvent, and it has the following effects. And you already knew this. I didn't even have to tell you that you can reduce the freezing point of a solution because you know that they ice the roads when it's supposed to ice, and they salt the roads when it's supposed to ice, and that helps lower the freezing point, helps make all that ice turn to liquid, and keeps the roads safer for at least a dip in temperature. It can get so low that it won't matter, but it will definitely make that water freeze at a lower temperature and hopefully keep it as liquid water, not solid water, when you're driving on it. So the reason that works, if you think about any liquid, here's a liquid form, and when we cool it off, we have to take energy out of all those things because they're moving around so much, and we like for them to be in this nice, neat, solid structure here. And that's awesome when that happens. But the problem is now we have these little impurities in there, these little dissolved, non-volatile solutes, and they kind of make it harder for everything to line up. If you look here, everything's not lined up, and it requires you take more energy out to get everything to line up properly. So you reduce the freezing point by having an impurity in there that's non-volatile. So notice also that the number of things you have will affect this, right? If we had 6 of these, it'd be even harder. If we had 2 of these, it would be a lot easier for this to happen. So the number of little particles you have affects what happens here, and we'll talk about that in a second. Now, increase of boiling point. What happens here? It's harder to achieve a vapor pressure equal to the atmospheric pressure, and this is actually the definition of boiling. And next year we'll talk about that when we do phase changes. It didn't really come up this year, but that's the definition of boiling. So what you need to do is have the things, the liquid in your container, have a vapor pressure equal to the atmospheric pressure, the pressure happening above, so it can kind of push it back. This is why the boiling point on top of a mountain in Colorado is lower than the boiling point at sea level, and that's because the atmospheric pressure is high and it's not pushing back as much. So you can boil water at a lower temperature. Anyway, I digress. The point here is colligative properties. And colligative properties happen because, again, we have these dissolved, non-volatile things. So these things don't want to move. They're rock solid. They're like salt and sugar and whatnot. They don't want to leave. And these water molecules are trying to leave, right? So if anything else, if you want to just think of it as these balls here are getting in the way of the water leaving, that's fine. I should probably turn that to blue just so that you're not confused, right? These balls here are preventing the water from leaving. It's making it harder to boil that water, so the boiling point's going to go up, okay? And that is pretty much a good understanding of why that happens. And again, if you had more of these blue balls here, more of these, if we had another one here, here and here, it's going to make it even harder. So the more you have, the harder it gets to boil. Just like here, the more you have, the harder it is going to be to freeze. And because of that, we have this important concept of ionic compounds are really good at these colligative properties. Metal, non-metal, because they dissociate. They turn into multiple ions when you put them into water. And by putting them into water as multiple ions, that's going to have a bigger effect. So we could salt our roads with sugar, but the problem with that is when you dissolve sugar in water, you get one unit thing, one molecule, aqueous. However, when you dissolve magnesium chloride, which is actually what they use to salt roads, you get an Mg2 plus aqueous, plus you get 2Cl minus aqueous. My daughter's about to walk in here from a movie. Hopefully she won't be too loud. NaCl, when you dissolve that into water, you're going to get, because it's ionic, metal, non-metal, you're going to get 1 Na aqueous and 1 Cl aqueous, and that's going to be 2. So here, look, you have two particles for the price of 1 because it dissolved and broke up into 2 particles. Here's aluminum nitrate. That's going to break up into 4 particles, aluminum 3 plus, and it's also going to make 3 NO3 minus. And that is going to we now have 4 particles. So this will break up the freezing point even more. It'll bring that freezing point down even more, and it'll bring that boiling point up a little more. All right, so that is the unit. I'm going to stop talking so you don't have to listen to me anymore. And please let me know if you have any questions. I will talk to you later, kids. Bye.